and we will address okay, so we will basically start with the planning of a network, and we will touch on all the aspects that need to be addressed during a DVB-T2 network planning exercise. So that will be the first part where we go through the full DTT network planning procedure. After that, we will look just and recap the differences between the T2 network and the T1 network, as well as ATSC3 network, which shows slight better improvements on DVB-T2. But I just want to highlight that. And then lastly, we will then look at a full implementation, and we will use the South African case and just address all the aspects that need to be looked at during such an exercise of DVB-T2 implementation, and considering not only technical aspects, but also other aspects, which is important. So we will start now with the setup of a planning system and just highlight the things that's required for such an exercise. Obviously, there will be lots of training on the specific planning software, whether it is ATDI software, whether it's RAP software, or LS Telkom software. Okay, so we will just use this now, the Cheer Plus BC program, as a typical example for planning and what's required. So if one look at planning of a specific service, obviously, if we are looking at T2 or T1, you will have to make sure that your planning software has got that specific module in order to do such planning. You will see that typically there's many other services that can be considered in such planning, and some tools are even broader than this, where they use one tool to fit all, but it makes the planning obviously more complex. Yes, we've got leg back here. This is just for information. This is between aeronautical services and broadcast services. So we obviously need a powerful database of all the stations or the transmitter stations that's available in the country at that time, whether it is analog TV, digital TV, and then also all the neighboring countries. You will definitely require a graphical user interface or geographical information system information, which will include map data. It can include population data, and it can include, yes, also information on the neighboring countries. Then specifically for DVB-T2, we definitely need to look at the GO6 plan and all the DTT information that's in that for your country and all other countries that falls within the coordination distance vector for your country. Then I will typically not do too many contour based calculations, but if you look on the center here and you see the map there, this is the typical sort of contour calculations you can do just to give you an indication of the coverage. I will typically prefer something more to the right here, where you get the actual coverage area. But depending on what the requirement is, you can use contours as well for display purposes. Then, obviously, there's the whole procedure of coordination, which one need to look at when you implement such new frequencies. You definitely need to look at what you are trying to propose, go through a planning exercise, and make sure that you do the coordination with neighboring countries, and then once you agree on it, you will go to the ITU for notification. So then at the same time, The network planning and optimization is very important, and we will look at that in more detail. We will look at what's the different parameters that can be changed, not only from a DVB-T2 perspective, but also just general aspects about your transmission equipment. Yes, then we will look at the frequency planning. We will look at the population analysis. Okay, so if we look at the information that you will require for this whole planning exercise, you will definitely have to look at getting the ITU information imported into your system, and make sure that you know exactly what has been coordinated during the last World Radio Conference or during your last interaction with the ITU, and make sure that you've got the frequency information, the channel, the ERP, the antenna patterns, etc. So with the transmitter information that you receive from the ITU, there should be an import facility that you can import that into your system. And that normally works quite well, because there's different import formats that's available, which will just accept the data very quickly. Then if you look at the typical parameters that we are interested in planning such a DTT or a DVB-T2 network, there's obviously the name of the station, the country where it appears in. So if it's a neighboring country, D will be for Germany. And so every country will have its unique code. It will be the coordinate of the actual station. It will be the antenna height. It will be a height above sea level of the site. And then you will also create effective heights, which the system will use the background data terrain model to actually create this for 360 degrees every 10 degrees in accordance with the ITU requirement. Then obviously there's frequency information, there's your polarization information, so whether it is in the H-plane or the horizontal or the vertical plane, polarized plane. So that will tell you how much power is being transmitted in that plane. Then if you've got a single frequency network, you will have a unique single frequency ID. And so if that unique single frequency ID will then appear at all the stations that use that same frequency, which is synchronized in the network. Then there's also a parameter regarding time delay that you can introduce to simulate networks and to reduce interference. Then you will have a pattern, and this pattern will be your horizontal pattern and your vertical pattern. And you can also then display it at the bottom as a 3D pattern, which you can more or less see how it is transmitted from the mast. You will have the service ID, and there it's clear that it's DVB-T2, and that's how it will appear in your actual database. And then for operational status, each country use their own namings for operational status. We will typically use SPA for spare, OPE for operational, LIC for licensed, etc. Okay, then what is important for planning of any of these networks is obviously the terrain model, which is very crucial. And one can normally configure that within your system. So you will have a data terrain model, but you will also have clutter information. And the clutter or morphology information is the typical land uses that's defined, whether it's a water area or it's maybe a forest area, a dense urban area, etc. Because those sort of information is used for attenuations when one is doing propagation. So you will typically couple a attenuation factor and a height to your morphology, and that will be used when your propagation model is activated to determine the signal strength or the interference signal at a distance. Okay, so again, if we look at the essential maps is definitely the topo information and the morphology. And then when you want to do such planning, it's typically required to have a 100-meter DTM, 100 by 100 meter resolution DTM, or better, maybe a 50 by 50. For practical purposes, yes, you can go much higher in resolution, maybe to 10 meter by 10 meter, but then your calculations will be very slow, and it's not recommended to use such a high resolution DTM in your first set of calculations. Otherwise, you will be sitting in front of your computer for quite a while waiting for results, where you can get a good indication of what's actually happening with your coverage or interference just by using about 100 by 100 meter DTM. Then obviously there's other maps which is nice to have, and that will be a political world map which show you the borders of the different countries. And then it can be all other types of maps, but you also have the opportunity to actually use Google Earth in the background, and then you can zoom in, or you can have OpenStreetMap, which is at different resolution levels, and that will give you very good information for specific areas where you are concerned about coverage, and to identify those very small areas which is uncovered. Then you can also have street maps, you can have population map information, and the population map information can be input into your system on a district level, or on a city level, or on just a grid level, to give you the population in a certain area. And when you do a coverage, you can get the total population within the coverage contour. Okay, so if one is doing a DTT network, then obviously one will have to look and see if this is maybe just on a city area, or if you want to do it national-wide, you can define with a polygon. You can define the area for calculation, and you can then define it, you can then activate it, and it will then just do coverage within a certain area, or you can just use a block and indicate the area of interest over a certain area like this. Then it's also important to know that if you are looking at planning, say in a DTT environment or a DVB-T2 environment, you can have an allotment area, and the frequency will then be an allotment which can be used over a large area, but it depends on how it's registered with the ITU. You can also have a single frequency network defined as a number of frequencies, the same frequency being used at different locations, but being connected to one another by the actual single frequency ID. And the system will typically pick that up, that it is a single frequency network, and you can display all the stations. In other cases, if it's an allotment area, it will be a vector, and the vector will indicate that this is an allotment vector for a certain frequency that can be used within that area. Okay, so if we look at the definition of planning parameters, the most important things to define is, yes, what kind of network? Is the single frequency network, or is the multiple frequency network? What kind of service are we looking at? And this is also very important. You look at fixed reception, you look at mobile reception, or you look at portable reception. So you will typically, fixed reception will always be at 10 meters above ground. Mobile reception will be at 1.5 meter above ground, and portable also around 1.5 meter. And you will see that the coverage maps look quite different if you do it for fixed or if you do it for mobile, just because of the actual antenna, receive antenna height above ground. Then obviously one need to decide if you're going to look at a local or a national wide network, where you look at the transmitted distances in between the sites. You will then obviously consider the guard interval, and you will look at your 1K, 2K, 3K, or 32K modes, which is better in some cases for certain types of reception, which is more applicable to that defined fixed or mobile or portable reception. Then what's also important, you need to look at what the future need is going to be. We are living in a very dynamic world where a number of years ago, analog reception was acceptable with a certain size of screen. Now we will very easily sit with an extremely large screen, and if you don't have the necessary resolution, which is defined by standard definition, high definition, or ultra high definition, then you will not end up providing the right sort of service to those customers. So there again, you also need to look at the code rate, you need to look at the modulation, and you need to look at the pilot pattern. So the reason why all of these parameters is important, it will also eventually result to a total bit rate per multiplex, and all the programs in the multiplex then will take up the total bit rate of the multiplex, which can be, say, in the region of about 25 megabits per second. And there again, we will touch on what is required for the different standard definition, high definition, also using MPEG or HVAC in the signal that's being generated at the studio. Okay, so then again, when we look at the reception mode, yes, you can be fixed. You can have fixed reception, which is always outside, 10 meters above ground. Then you can have portable indoor reception, portable outdoor reception, and there you just consider the attenuation, which is typically applicable for reception behind one wall, which is in the region maybe of around about 10 dB, or you look at mobile indoor or out, inside or outdoor, which there is again a difference. And many of these parameters, like for portable indoor and portable outdoor, will depend very much on the type of building material that's being used within your country, and one need to then build your model in accordance with those attenuations that's typically experienced in your country when you have indoor or outdoor reception. So yes, if one look at the future, then obviously if you're looking at vehicles which is automated, yes, the mobile outdoor and indoor inside will become very important, because that's the type of entertainment systems that you will have, and that will change drastically from what we have or we had a few years ago, and where the direction where it's going. So in these pictures, you can just see that you've got normally a setting where you can actually select the fixed mobile outdoor, mobile indoor, and portable reception. Okay, then what is important, you will, when you do the planning in a T2 network, there's a number of parameters which you can change, and this will all impact on the final capacity that you will have in your multiplex. And so you can see here typically the parameters that will affect it. So you can change your bandwidth, and there, if you look at T2, there's more choices in DVB T2 than there is in T1. You also have very narrow bands that you can use of 1.75 megahertz, or 5 megahertz, or 6, or 7, or 8. At the same time, you can also look at your FFT size, which will give you different sizes, and they are also very applicable to certain type of transmissions. And we will get to that to see what the benefit is of using different FFT sizes. Then guard interval, which we spent quite a bit of time on yesterday. So you can choose your guard interval to suit the type of network that you will be building. And we will be typically in doing a national plan, we will go for the largest guard interval of maybe around about 1/4. And that should, with T2, give you 159 kilometers distance that the transmitters will only start experiencing interference. So if you've got transmitters over that, and you've got a receive point, then the difference in that distance from the one to the other, if it's more than 159 kilometers, you will start experiencing interference. But that is, in our environment, you should be more or less interference-free if you've got a 1/4 guard interval. Then you will see that the pilot pattern, depending on the configuration that you choose, only certain pilot patterns will be acceptable for the receiver, because the others are disqualified because the system will not work with certain combinations of transmit configurations. Then again, you can look at your modulation. You can go for QPSK 16 gram, 64 to 56 gram. And you will also see when we get to ATSC3, yes, you've got higher grams that you can use there. The code rate or forward error correction, that's also important. And one need to go for a typical code rate. And you can also look at the standard configurations, which is recommended by ITU, for a combination of transmit parameters, which has been tested worldwide. So one can use the guidelines from the ITU in that. And then receive conditions fixed. There again, you can select that. And this eventually, this combination will then give you a capacity of the transport stream, and it will also give you the E-min-met, or the minimum usable field strength for a certain percentage of locations. Okay. Okay, then there's obviously very practical things that one need to consider, and we will just quickly just look at those sort of things which will be normally be taken care of by the signal distributor who provide the actual network, and that will not be as important for the regulator as it is for the signal distributor. So if we look at that, yes, then obviously we need to look at the space on the mast. Is there space for an additional antenna if you have not been using, say, UHF on the mast, and you have got a VHF section and maybe some FM antennas below, but you don't have enough space for a 4-stack and 4-bay panel antenna system. You also need to look at the diameter of the mast at that point, because you need to know that otherwise, if the mast is too wide, you will have big nulls in between your lobes, and you might end up with not good coverage in those areas. You obviously need to look at the space that's available in the transmitter room. You need to look at the infrastructure. You need to involve a civil engineer to look at the wind loading on the mast with the installation of new antennas. You need to look at the cable trays for the feeder cables. Yeah, and any other capacity limitations. You need to look at your air conditioning that's available to make sure that you can keep the transmitters within the operating temperature range. And that can be achieved either with air conditioning or with ducting that will remove the warm air outside the building. Okay, then obviously, if you start looking at your transmitter sites, you need to get a good feel for how good this antenna site or this this site is before you actually install a mast or an antenna system. So you can just do field strength contours, and these field strength contours will quickly give you an indication how suitable the site is for your transmission. Okay, so if we look at planning in general, it's important to understand the principle of field strength, coverage, interference, multiple interference, etc., and see what the effect of that is on your actual your coverage area that you can achieve. Because at first you will just decide on a certain point, and you will, on a flat earth, you will get a circle coverage. So yes, there's obviously what's important is your noise level, because if we look at the parameters we looked at yesterday as well, for certain types of reception, maybe in a mobile environment or so, you will need a certain C over N that will give you a certain number of dBs in order for that receiver to receive the signal. So yes, you also have got your transmit point, and you will see that the level, as you go away, drops off and eventually drops into the noise. And that is in a circular manner all around the mast. You've got your noise level there, and then you've got your location, as you can see, where the antenna is actually indicated right in the center there. So, as we've said, yes, you want a certain C over I to receive a certain defined signal, because that C over I will ensure that you can, say, receive a QPSK signal with so much forward error correction and so many carriers. But that differs drastically, and we will also see that you can have a signal to noise of maybe 6 dB for a very low capacity network, but this can also go up to about 26 dBs or more for a large capacity network, which is not so robust. Okay, so effectively, once you've got your C over N for that specific constellation and configuration of your transmitter, and where this cuts your free space loss graph, you actually then determine the coverage that you can achieve. And in this case, we are not looking at terrain at all. We are just looking at the flat earth, just to demonstrate the principle of field strength and then also interference. So, yes, what we have here is then just, it's a field strength contour, and the field strength that you've got there is equivalent to the coverage area because there's no interference. When field strength get affected by interference, the coverage area will not be equal to the actual field strength calculation. Okay, so we've got the same situation as we've had before. We've got our C over carrier to noise ratio. We've got our free space loss graph. We've got the transmit antenna right in the center. And what we do now, we add another transmitter. Now, this is specifically to demonstrate MFN network where you've got another transmitter, and this transmitter can be co-channel or it can be adjacent channel, but which has a certain effect on the existing transmission. This can also obviously represent two countries where the one transmitter is in one country and the other one in a different country, and the protection ratio will be defined in accordance with the relationship between the two frequencies. So we've got one transmitter there, we've got another transmitter some distance away, and now we can see that, yes, there must be some effect, because we can see at some points the signal strength from the wanted transmitter is higher than the other, and in other cases it's lower than the other. And so the next thing to look at is the protection ratio. So again, I spoke about protection ratio yesterday, and we said that for co-channel, for co-channel in the digital network or a DVB-T2 network, we need approximately 20 dB. So the level difference from there to there is 20 dB. So you need to be higher 20 dB than the other signal in order to have reception. So we can already see that there's a definite problem here, because if we look at this point, say there, where the minimum received signal is, and you go up there, this signal is already, say, 10 dB higher, and then you still need a 20 dB for co-channel. So this transmitter will suffer severe interference. So the resultant curve that you will also then draw for your interference will affect this transmitter. And then you can see what actually happened if you introduce that transmitter. It actually reduces the coverage of the wanted transmitter to a fraction of the whole area that you want actually coverage in. So this is not a good scenario, and there's obviously various ways of getting rid of this, and probably in an MFN, the best scenario will be to change the frequency and use a frequency which is either adjacent channel with less, a smaller protection ratio, or even the second adjacent channel, which will not be affected. So we will just now also demonstrate further interference, where we've got more than one interference. We've got FD, we've got F1 and F2, which is being deployed there on different distances away from this wanted site. So there we've got the same principle. We've got a certain protection ratio, and then we expand the curve for the protection ratio, and then we get to a usable field strength, which is because you've got more than one affected or interference, and that's summarized in the actual effective usable field strength, because this is now a nuisance field that's introduced there. And then you can see coverage with noise only is that area, and then now coverage area with several interferent TXs reduced to a very, your coverage to a very small area. So what you can also learn from this is that in many cases you will have, you will be far above the minimum usable field strength, but if you can overcome the minimum usable field strength and the protection ratio, and your wanted signal is higher, like we can see in this area, it's very high because this is your level indicator. You can still overcome the interference, and you are then having interference-free coverage or interference-limited coverage, where if there's only noise present, it's noise-limited coverage. So if we look at usable field strength, sorry, it measures for the interference situation. Usable field strength also take into account combined effect of the entire, the entire or all of the interference transmitters. So that affects the usable field strength. And then also, it also takes into account the man-made noise, that C over I level, and the noise below it, It's independent of the characteristics of the wanted transmitter. It's affected by the interference transmitters. It can be determined for any location. And this is very important. So if you don't have a planning tool and you need to do this manually or with a very simplistic planning tool, your results will not be as accurate, and you will struggle to do the planning in a realistic time for your country, say for DVB-T2 implementation. Then large usable field strength means high interference level, so it's directly related to that. And you will also see that for each technology, there's a summation process that's required. And we will talk about the summation processes as well. Okay, so the summation procedure, typically type of the typical ones is non-statistical methods is maximum procedure or power sum method. So it's the sum of the squares of the individual interferers. And then if you look at statistical methods, and many of the digital transmissions also is typically log normal method. FM can be multiplication method, simplified multiplication method, and simplified log normal method, and then integration method. So there's various summation processes, and that is to add up the total interference from a number of transmitters that's affecting the wanted transmitter. Okay, so then, yes, we've mentioned protection ratios now a number of times. So the definition is the RF protection ratio is the minimum value of the wanted to unwanted signal, and usually expressed in decibels at the receiver point. So that is the protection ratio that you will require actually to have reception at that point. It's determined by specific conditions, such as the specific reception quality that's achieved at the receiver point, yeah. Okay, so what's also important, protection ratios is dependent on the actual frequency difference between the two. So you will see that for co-channel, yes, there's a specific protection ratio. With analog systems, we could improve the co-channel protection ratio with stability in your frequency system and also offset. And then you can change that in order to limit the interference of two transmitters, which is co-channel, just with a certain frequency offset and then also stability. But so we will have then co-channel interference scenarios, which is typically a very high value, and then adjacent channel is much lower. So the effect of the adjacent channel is obviously not as dominant. And then we will have the first, the second or third adjacent. In our environments, it's not so crucial. We will only look at the first lower or upper, so the plus minus first adjacent channel. Then in the past, the image channel was also an issue, but nowadays it's, in most cases, I haven't found many planning scenarios where we had to cater for the image channel, which is the lower mix of the sound and the video carrier, and the upper one. Then obviously overlapping channels, that can also be a case where you've got maybe the one country is using a certain channel bandwidth and you are using a different, then there's just an overlap between the actual transmissions, because you've got the one is using maybe a 5 megahertz channel bandwidth and the other one is using an 8 megahertz channel bandwidth, and there's some overlap. Then there's also protection ratios then for a digital signal with an analog signal. But the digital signals are typically much more robust against interference than your analog signal. So the analog will first be affected, although it might not disappear completely. You will have digital to analog, maybe 45 dB or so, and vice versa, you will maybe only have a 20 dB protection ratio. So this is more robust than your analog signal. And then in cases where aeronautical, where FM and aeronautical bands meet, there's also a consideration of looking at the protection ratio between your aeronautical service and your FM service and vice versa. And obviously, the most crucial one there is the one in the direction of the aeronautical service, because the aeronautical service is critical communication, and that need to be protected against interference, because it will affect your aircraft. Okay, then if we look at the network planning aspect, so you will first have to do a field strength calculation, and the ones of you who know planning tools, there's always different propagation models. So you need to define that propagation model, and you can select it. And there are certain propagation models which is again better for a certain area than for other areas. And there again, by doing some checking and measurements within your country, you will identify the propagation model which is most suitable. Okay, so like we've said before, yes, the receiver height is also very important, and receiver height can either be adjusted in your field strength calculation by selecting the height of that receiver, or you can use 10 meters and you can use a statistical reduction in level And for that, you can do that by ticking just a box in the network processor. One need to be careful that you don't do your calculations maybe at 1.5 meter, and you've got the box tick for a further reduction because of a theoretical reduction, because then you will end up with a much smaller coverage area than you actually need to have just because you applied that reduction twice. Okay, and then obviously the resolution will also play, the resolution of your DTM will also play a role in your accuracy of your predictions. Okay, so if we look at a typical network analysis tool, there's various things that will affect it, and this is apart from the previous slide we saw a while ago, where we actually look at the pilot pattern and you look at the QAM modulation, etc. So just with general RF, with your radio frequency, without and just looking at propagation, you will typically have a minimum usable field strength at which your receiver will lock. Then there's your height loss. So if it's disabled, you will do your calculation in your first calculation at the specific height that you want your receive antenna. If you've done it at 10 meters above ground, you can include the height loss calculation, and that will then be determined by the type of receiver mode that you're in. And it will look at the different heights the receiver is adjusted on, and it will then do a correction. So this is your E-min met then for 50% of the time. And then you've got time location also coming in, because you want a certain number of percentage of time you want the signal to exceed a certain field strength. And then this is corrected. So you might have minimum E-min met of 36, but because you want 95 location probability, it pushes it up to 45, because that's for 50% and this is for 95%. So that's also a statistical adjustment of the level. So you will also find this location probability in your DVB-T recommendation. If you were planning for TDAB or so, that, as far as I remember, it drops to 90%, and then, yeah, you use 90%. That should be accurate enough for DAB coverage. Then obviously you need to choose the bandwidth of your channels. And here you can also play around with, if you've got a typical, if you define the typical receive antenna, your receive antenna will have a certain pattern. And if the antenna is pointed at a different transmitter, and you use that antenna for your typical reception, you will have antenna discrimination. So it will look at what the attenuation is on the antenna in the direction it's installed, and it will add that additional, or it will subtract that from the actual received signal, because you will be losing some signal because you're not aligned with that antenna to the actual transmit antenna. Then if you look at polarization discrimination, so if say your analog network, you are using those antennas, and they were all for the UHF band, but they were horizontally polarized, and now your digital signal is vertically polarized, you can tick that box, and that will automatically then look at the two transmissions, and it will know that it needs to apply around about, say, 16 dB for UHF antenna loss because of the difference in polarization that you are using. And then you've got a further box here where you can use actually your own protection ratios between services that you've defined or optimized through studies that's being performed. Then on this side, you can just see the wanted summation, the interference summation that need to be used. And you can always go to default, and it will take the default as it is defined in, say, the GEO6 parameters, and it will automatically default to the initial settings. Yeah, you can define your fixed reception or mobile reception or whatever. We talked about this as well. You can look at the set-top box or the integrated digital receiver in your television. And if you know how that receiver in your country is defined, you can go for minimum delay, maximum, or main focus, and select that because that will also have an effect on the resultant coverage area and interference scenario. Then here you can see, because this is just your network analysis from an RF perspective, but here you get your information which you can access and define there under your T2 system. So it will tell you are using currently a 16 QAM modulation, 2/3 forward error correction, 8K carrier scheme, and 1/4 guard interval, and pilot pattern 1. And there's no implementation margin. Sometimes you want to introduce an implementation margin to cater for additional losses within the system or to calibrate your propagation model. Okay. Okay, so apart from those parameters, which is all important during the planning process, one also need to understand that there's different results that can be produced. And these results are extremely useful in making your planning process simpler and to analyze interference and to look at, make sure that you don't have too much coverage overlap within the system. So for that, you have all these different results. You also have specific results, which is the SFN, which is single frequency network results, which also assist you with the single frequency network results. And you also have got information selection there where you can actually look at more detail of what's happening in the background. But as far as I can remember, there is a slide somewhere in the presentation that will tell you a little bit more about that additional information that you can get to actually see what will happen with the synchronization of signals in the background. Okay, so yes, if we here look at the network analysis and we are looking at the single frequency network results. So you've got your single frequency network coverage, your best server coverage. So it tells you which is the best transmitter at that point. SFN number of best servers, so that's the number of servers that will exceed the minimum usable field strength. Here you can look at your signal frequency level gain. That's because of signals falling within the guard interval and being added and acts as a gain for your single frequency network. Then you can also get information on the strongest interferer, potential interferer. And then you can look at, so that's the strongest interferer but it's not to say that you will have no coverage. Then you've got another one which also bring the coverage into account, and we'll see if you've got, if you don't have the necessary protection of the protection ratio, and which will cause no coverage. And then you also have one which will tell you how much headroom you've got, and this headroom tell you how much the signal can actually reduce before you have no coverage. Okay, so this is just a typical scenario. So what we've defined, we defined here the contour, which tell us what the area we're interested in, and we selected a certain number of transmitters, or only one transmitter, and this is the resultant coverage of the single frequency transmitters you've got there. So I will mark all my transmitters, I will do individual coverages, and I will combine the coverages considering interference between them and signals being in and out of the guard interval, and I will end up with a resultant coverage. And so the gray area will tell me where I've got the maximum sort of coverage. Then I can also, I can also look at the base server. So we see a little bit more about the network. We can see there's definitely one transmitter, there's another transmitter, there's another transmitter that's providing this service in sort of orange, and we've got one in green. So now you can see where the signals from these transmitters is the best server for the area. So that tells you a little bit more about the so this one tells you information, number of base servers. So it will tell you how many transmitters you can receive at a specific point. So there you can actually then determine, okay, in which direction we need to turn the antenna in order to have that best reception. And this sort of information is very important for your installers. And when we go to the practical and the use case, we will see that you need something like this on a national basis available for your installers, that they don't struggle to find a certain transmitter because they think that's the best server. If they're in the purple area, they will know, yes, I need to tune my transmitter to Munich. And if I'm in the brown area, it will most probably be, it's definitely another site, and in the green area, it's another site. That will just make it so much easier for the installers. And apart from that, if you then in an uncovered area, you know that if I'm situated in that area, I don't have to worry. I can't receive the signal there, and I will probably have to install a satellite receiver and look at satellite to cover that area if the alternative is available. Okay. Again, with all of these, you will always have a legend that you can display, and the legend will then tell you what the color coding is, and maybe where it's yellow, you will have 3 dB gain, where it's light blue, you will have 2 dB gain. So this just gives you an indication of the single frequency network gain that you can experience. Okay, this again just gives you an indication of the potential interference, but like we can see, it's just potential interference. It's not removing the coverage. So there's still coverage, but you will just know that there is a signal in the background that can cause interference, and that might be due to the guard interval. And if you then select info on this picture, you can then see a graph and you can see if that interference is outside or inside the guard interval. So obviously, if it's outside the guard interval, it will be interference. If the signal is inside, then it will only add to the signal strength. Okay. Here you can then see, okay, no coverage. So it will give you the actual areas where there's no coverage. And then if you now move over this, then over these areas, you will again in your legend see maybe 10 dB or 15 dB, and it will tell you what the coverage reserve is, how much the signal can drop down or fade before you have no coverage at that specific point. Okay, so yeah, this is now what I've talked about, the tool tips. So you can select by clicking right on the map, and it will give you the levels of the different single frequencies that's being received, and you will see what the difference is between the paths that it's running at that point. So this will be, if I take this measurement at this point, there will be a 68 or whatever microsecond delay between those points, but the guard interval is bigger enough, and that will ensure that I've got, sorry, I just want to switch this off quickly. Okay, so yes, at this point you can see this is the guard interval that you've got, and you've got more than 275 microseconds that you can play, and there's no interference except there at that point where it can cause interference, potential interference. But you will get a very good indication of what's actually happened with your network at that point, just using your planning software. Okay, so then there is further a further tool you can use, because you can now, if you sit with the interference scenario, you can enter in a single frequency network, you can enter delays, and the delays will then delays will never remove interference totally. It will only shift it, because if you put in a delay at one point, it will affect it. There will be a bigger effect on the signal in another area. So you only move away interference with entering of delays in the feed signal of one of the transmitters. What you can also do to get rid of interference, you can adapt the antenna pattern. So you can put a null in there, and you can play around with your software, or by changing the patterns. If you are applying this to a neighboring country, the planning procedure will automatically tell you how much you need to reduce the antenna pattern in a certain direction in order to get rid of interference onto your neighbors, and to ensure that you can introduce or can coordinate your frequency with your neighbors and notify the ITU. Okay, and then lastly, you can obviously also change your effective radiated power, which is the antenna gain, which is the transmitter power minus the feeder losses and other losses, plus the antenna gain. Okay, then thirdly, you can also you can change the tilt of the antenna. So you can put in a large tilt that the maximum of the signal is not reaching the far lying areas, and you just reduce it to limit potential interference. Okay, so yes, we've talked about now a single frequency network, but obviously there's always also potential of analog interference. So what you will do typically in a scenario where you've got a single frequency network with a specific type of transmission, maybe DVB-T2, and you've got your analog signals. So in those instances, you will create C over I's coverage over interference scenarios. And then you can actually create a picture, because now you use the correct C over I limit for an analog and a digital signal, and you can combine that then with the C over I results from the digital to digital networks, and you can then have a network, do it in the network processor, and then get the full result of the actual interference, considering the analog and the digital signals. Okay, so here's it's just an example of how the analog signals can affect the digital signals. So you can see here at that transmitter, yes, there might be an existing analog. Typically, it would have had the blue coverage, but now because there's interference, it reduces it in those areas just to the green area. Okay, so you will see that in any sort of network deployment or conversion from analog to digital, you will always be confronted with existing transmitters and new transmitters. In very few cases, it will work that the two are not on air at the same time. So when you introduce your DVB-T2 network, you will still be sitting with analog services. So you might have a plan where you will first keep certain stations on air on the existing frequency. You might introduce a different frequency than the final frequency for your DTT network. And once analog is switched off, you will, through a coordinated process with the viewers, inform them of the frequency change, that it's as unintrusive as possible to them, and will not cause unnecessary loss of signal where they're not informed about the change in frequency. Okay, so again, yes, you can, there's a procedure defined here where you can actually protection of already existing services. So you will do an interference transmitter calculation to find out the possible interference on a digital signal. You can do a wanted transmitter calculation for each of the interference stations. So wanted is obviously you take them into consideration to see how they are affected, how the other stations will affect them. You can calculate the usable field strength with the new stations and without the new stations, and you can see what's happening in the network. Then you can calculate the increase in the usable field strength. And then especially for coordination purposes, you can see if it increases the usable field strength with 0.2 dB or 0.5, depending on what the regulation is saying in that specific area. And then you can ensure that you maybe introduce a different antenna pattern, or apply something else which will reduce the transmission into that direction. So again, the main point we want to make here is to say, yes, transmissions need to be protected, especially in neighboring countries. And if you look at the right here, so if you do such a calculation between the wanted and the unwanted signals in the neighboring country, you will come up with a converted antenna pattern, which will tell you how what the antenna pattern need to look like in order to limit the transmission into a certain direction, and that you can then coordinate your frequency with your neighbors and notify the ITU. Okay, so there's specific application where you can actually simplify these calculations depending on the software that you've got. And yes, it just makes life much simpler for you to look at interference in neighboring countries. Like you can see here, it's between Czech Republic, Germany, Austria. Yeah, and here again, it will give you, in this calculation, it will tell you what the interference field strength is at those specific points, because you will create certain points, test points, and depending on the procedure that you've got between you and your neighboring countries, you can highlight those test points or introduce them and see what has happened at those test points and how much it increased. And then you need to take the steps to ensure that you don't increase the field strength with more than what the agreement between you and your neighboring country is saying. Okay, so here again, conformity check, that's got to do with mostly with bilateral agreements that will be entered in the frequency plan, say the GO6 plan, and then there's a specific procedure that need to be followed, and this will tell you how, if it can be implemented and if it can't be implemented, and then also looking at what you need to do to reduce the signal strength. Then, if one just look at the conformity check, and you are looking at if this station needs coordination, you will apply these coordination contours, and it will tell you. So if I do it from a certain station, it will tell me that where this contour is activated or it's crossing the border into another country, I need to coordinate that station with the other country, and I need to go through the agreed coordination procedure, because this will just tell you that you need to coordinate with your coordination contour that's being developed or calculated. So here again, you can see the interference field strength in France, in Switzerland, etc., and you can they need to take steps to actually reduce that. Okay, then generally overlay of street maps. So if you can visualize all your results that you produce in your planning system, and you can overlay your maps on a street map. You can also, like I've said earlier, you can use OpenStreetMaps, or there's a number of formats that you can use, and then you can go down to street level or even house level to see what the situation is on the ground. Then what you can also do, if you've got your population information in a layer, you can do various calculations. You can do calculations on a vector basis. You will have then the results of the files, and that will tell you how many people is eventually in a certain area. You can see here, so the total population is 3.4 million. The covered population is 3,305,000, or sorry, 3,056,000, and it's 88% of the area. And then it tells you what that 80% of the total area is, and then the covered area in square kilometers and the covered area in percentage. So these population maps are very useful for various analysis, especially if there are strict recommendations on how many people need to be covered within the actual area in your country. So this again, it will give you the individual information of a specific area, and depending on your information that's available from your Department of Statistics in your country, we can introduce that into the planning to make sure that you've got the best resolution of data during your planning exercise. Okay, then you can also export the coverages to Google Earth. And we've seen that many people prefer to use Google Earth. They use it as a planning tool with the resulted coverage results that's just opened in Google Earth. And by switching certain images on and off, you can get very useful information. And you can also use it in a presentation to demonstrate the outcome of the planning exercise. Then what's also important, one need to be very practical in this planning exercise. Maybe from the regulator perspective, you will not always go into this detail, but for an operator or a signal distributor perspective, they will go into very much detail. They will look at the ERP or in kilowatt or in watts or dB watts. You will look at the antenna pattern that's being used, antenna gain. You look at the feeder cable that's being used. You look at the feeder cable losses, the cable length to get the total loss. You will put in connector losses. You will put in feeder losses. You look at the transmitter output power, and then you will get an effective output power. So this is very important, because you can also use this then to determine what the transmitter output need to be in order to reach the agreed or planned transmitter power by using certain antennas and reaching your coverage as you've planned it. Okay, so now we've reached the end of this first presentation, and you are welcome to ask questions. If there's any questions. Yes.
Hello, Mr.
Yes, I'm here.
Yeah, really, I'm so happy to attend this lecture. Really, so happy. I'm asking about software you can use it to coverage planning. Have any software free?
Yes, we've got software. Our software is called Chill Plus BC, and it's actually quite an easy software to use, because it's got all the protection ratios built into the system, and it makes the planning aspect quite easier. But there's also training going with it. to ensure that you can get control of the software easily. The training on the software can be given virtually. So we've got very practical solutions for planning and training, either in person or virtually.
Yeah. Okay.
Yeah, you can. I think one can use SMS for DC as well, but obviously it's limited in its planning capability. You can use ATDI software. You can use RAP software. So there's a number of softwares that you can use. We think that the LS software is probably the most comprehensive because it takes interference between different networks into account, and it does it automatically. You just need to apply the correct procedure.
Okay, you can account the population in area.
You can count the attenuation.
Calculation.
Yeah. You can do you can do coordination. You can do coverage, attenuation, interference. You can do all of it. Yeah.
Yeah. Okay. Thank you.
Thank you.
Hi. Good morning.
Good morning.
I have a question about the map. Is the map on the software up to date? Does it have the latest map according to the buildings and all the stuff?
It all depends on
to make a map coverage. I mean, does the buildings are up to date?
We can get all updated maps. So we will provide some standard maps with the system. If you want very detailed maps, we can also get that, but there will be a cost associated with that. But you can really get excellent mapping. But sometimes it's not necessary to go to such the best, maybe one resolution, 1 meter by 1 meter resolution building information. You can get away with much cheaper information with as accurate coverage results. So we will make a recommendation for you on what the best is. Because if you are planning microwave links, then obviously you would like to know what's in the way of the microwave link. If we are looking at a single frequency network where there's coverage coming from different areas, and we've got that area defined as a density area, we will consider it well in our calculation, and our accuracy of the coverage will give you a good indication if there's coverage or not. So we are not doing microwave planning with this. We've got another tool to do microwave planning. But I think in most of these instances, you will probably have the feed arrangement with satellite, and then you don't have to do the point-to-point planning. I hope that answers your question.
Or maybe we can import it from Google Earth. There is some compatibility.
Yes. Again, with Google Earth, you can have an overlay and you can see. Yes, you can see what's happening in the background there. Yeah.
Hello, good morning.
Hello, good morning.
Please, sir, could you go to the slide number 33 and if possible to re-explain the figures?
Okay. So this is just an example, but you will set up your planning tool, and it will have a certain receive condition. So it might look at minimum delay, and you are looking then at a specific point where the signals, and there we can see now, we are doing it right at that point. So we are looking at that point and we say minimum delay, this land shoot is the first signal that's being received by the receiver at that point, and there's land shoot transmitter there. So it's receiving it, and it's set to minimum delay, so it takes that transmitter, which is the nearest. Then it will show you here that within the guard interval, this signal from Shannon C is also received. But it is within the guard interval, because that indicates your guard interval, the blue. And it's anyway, so it contributes to the signal. It's within the guard interval. It's not of a very high level, so it will contribute very little. If you then look at Munich, Munich has got a higher level coming in, and it will just show you again, it's within the guard interval. If we, I just want to remove this one. Okay, so here we can see that this Wendelstein, it exceeds the blue level. So there's a small potential difference, or a potential that it might cause some interference, because it is a long delay. So if we looked at it a little bit further, this blue line would have cut off and get down to the bottom here. So this is exceeding that level, and there is a slight chance that there can be interference. So this is just a tooltip. So if you are concerned because you want to see that there's maybe an interference potential at a certain point, you can just see and which transmitter is causing that, and then you can drop the level of this transmitter, and you can then, when you drop the level or you change the pattern slightly, it will not exceed that limit, and there's no chance of interference. But you can use it very well within a single frequency network as a support tool.
Okay, thank you.
Thank you.
Good morning.
Good morning.
Good morning. I have a question.
Yes.
In coordination, the level is different between country. For example, Austria 30 and France 40. Why? Why the difference?
Okay, I'll just go there. So there's okay, so in your there can be different agreements, because this is now, you can see at the top there, bilateral agreements. So if you're in Germany, you've got a certain level that's defined between the countries. So France said, no, it's not allowed to exceed 40 dB microvolt per meter at any of the test points. With Switzerland, they agreed on 35. And with Austria, they agreed on 30. So that just tells you what the different arrangements is with the bilateral agreements. So this is individual agreements between the countries, between these European countries.
Oh, okay, I understand. Thank you.
Okay, pleasure.
Sir, but the level of the level that for allocation, it is according to what? Hello?
Yes, sorry, can you just repeat that?
The level allocated to the country, according to what? To which parameter?
Look, what will normally happen, those levels, they will look at the existing situation and look at the level that's being recorded with the current scenario. Then, if you increase that level with more than 0.2 or 0.5, depending on what's applicable there, you need to coordinate with your neighbor. So in most cases, you're not allowed to increase the usable field strength with more than 0.2 dB. If you increase, then it actually, you need to take steps to bring it down. And that will normally have to be in your antenna pattern or your ERP with your neighboring country. But that is the standard ITU rule that will apply. If there is a bilateral agreement and they've put this and they say you cannot exceed, so they say you have field strength on the border, you cannot exceed the field strength on the border contour of 40 dB microvolt per meter. Then that's a bilateral agreement, and the two countries will live with one another according to that bilateral agreement. And they will then not object to the coordination of the frequency if you're below that.
So if I, for example, I have a problem of interference with my neighbor, so I have to notify it to the ITU, right?
Yes, you will have to inform the ITU that you've got a problem, and they will then investigate it and see if this is another transmitter. So they will send that country a letter, and they will make them aware of this complaint, and then they will, the country need to respond. And ITU can, with their database, also see what their level is, because these levels are determined normally in a very simple way with a simple procedure. And then if it exceeds that, then obviously there's a problem, and then that country need to react and come up with a solution.
Okay, thank you for the information.
Okay.
I have another question. If there are no bilateral agreement, what is the level in this case?
The level will be the existing level. That's
Yes.
as the stations appear on the database with the recommended power sum or summation method, and they will see when they do the calculation what it should be. And if they add the station and that level is increased with more than 0.2 or 0.5, depending on where the two stations is lying, it will not be accepted. So that's the general rule. Is the increase need to be less than 0.2 or 0.5, depending on where the two stations is. And also it also has got an effect. There's a difference between the TV regulations and the FM regulations. Is that clear?
Now it's not really clear.
Okay, so what we've said also in here, you will do a calculation.
Yes.
Leaving the new station out. So I will have all the transmitters on my database, and I will look at the interference, the summation of all the interference from my country at that test point, at the border point.
Mm-hmm.
If it is then increased, when I add so I first do one without the new transmitter, and then I will, after the first calculation, I will add the other transmitter, and I will see what's that increase. If it's below, if it's not affecting it with more than 0.2 dB, then it's fine. And the ITU will do the same calculation. Because then I will also, with my neighbors, I will I'll discuss it with them, they will agree, and then I can coordinate and notify the ITU that I've got agreement with the neighbors, and they will then go through their procedure to make sure that all parties are happy.
Yes, thank you.
Okay.
Excuse me, if we add a new station, an old operational SFN, what we have to do? do the synchronization, new synchronization.
Okay, so if you add a new station and you can see there's a synchronization problem, then you can simulate it in your planning tool and you can put a delay in the transmitter. So you now need to see if you just delay it because it might be arriving too early, but the transmitter that's, so you need to see what the timing is between the two. And then you can put in an additional delay, and then you can get rid of the interference. But as of you get rid of the timing problem at the areas that you're interested. But what I've also said is that you can never just remove the interference. You just move it around, and you need to move it to an area where it's not so critical. Where there's no people staying. So you can move it in that, but you will need a simulation tool to do that.
Yes, thank you.
A pleasure. Yes, you can see here's the procedure as well that I talked about earlier with a digital plan entry, where you go through these steps, and then if it's compatible, yes, you don't have to worry. But I will send the slides to you as well, and you can then go through that procedure as it's described. Is there any more questions? Okay, I see there was one. Okay, no. Is there any more questions? You can put the question if there is one. Okay, I see the question is, I planned a SFN in the past, and now I want to add a station. Should I need to reschedule it? All in the plan. Okay, so there's two situations. If it's an allotment area and the area is well defined and you want to add a station, it's pretty easy to add it, because there will be limitations on the power, and then you can just move ahead. If it's an assignment and you don't have that frequency in the plan, you need to do that coordination procedure as described here, where you first do a calculation with the existing network, and then you add your one station, and then you can see if it increased if it's compatible or not compatible according to the usable field strength. But in some cases, you might have a plan with a lot of frequencies, which is already coordinated with the ITU. And if that's already in the plan, you can just use it because you already coordinated it in accordance with certain operational parameters. Okay, yes, there's another question here. I have a question about the modulation in DVB-T, and I guess T2 as well. It uses the COFDM modulation, codoorthogonal frequency division multiplex modulation, but we can find like QAM or QPSK. in this case, what is the relation between the two types? So you will find that if I use QPSK, it's a very simple modulation, and I will get a very low receive signal strength. So you will be able, in that instance, if you use QPSK, you will see that effectively the capacity of your network will be very low. But if I change it to a QAM, you will get a much more capacity on your network. And so that's the basic explanation of the two. You will see in DVB-T2, they went up to 256 QAM, which again gave you much more capacity, considering that and some other parameters.
Excuse me, how to determine the test point in this slide?
Okay, in the test points can be on the border, so you will draw a line towards the border, the closest border, and you can then take a few test points on the border, and you can then confirm that there's no increase. With the bilateral agreements, it will also be specified in the bilateral agreement. Okay, there's a question on the synchronization. So if you have chosen the correct guard interval, and you've looked at your transmitter spacing, etc., because you will typically have a network with a certain spacing between the transmitters. So if one would have gone for a guard interval that will give you 159 kilometers between the two transmitters, then you are virtually free from interference, because there's very few times that you will have transmitters 159 kilometers away from one another, and then you will have interference. So obviously, we've also seen that with transmitters 67 kilometers from one another, with a guard interval of 1/8, there we had very, very little areas that experienced interference, because it's normally further than 67 kilometers. And then your signal has deteriorated in level that you overcome your protection ratio and that you've got coverage without any synchronization problems.
أنا أقول بس هارب منك.
كل المحاضرة. تمام كيف؟
يلا تركب ورقة.
جوزين ده؟
جوزين أنا برضه. طيب.
We will have another session just on where we compare T1 and T2, and then we can look again at the different parameters, and we can also look at the COFDM modulation and the effect of that. What I will also, I've made a note about the coordination and the actual points, and I will send you an article on that, on how that is exactly calculated and where the test points will be. as it's defined by the ITU. Is there any more questions, or shall I continue with the next presentation?
Yes, sir, you can continue.
Okay, thank you. Okay, I will just go through some variations now between T2 and T1. I had this slide up yesterday as well during the presentation. And here we can again see some comparisons. For example, if we look at T2, having the same EMIN and the same data rate. So if we look at, for example, a 64 QAM and a 16 QAM, and the FFT sizes are the same, the guard intervals are the same, the code rate are slightly different, and then the carrier is in extended mode, we will see that you can reach with T2 with the 64 QAM 25 megabits per second, and with the 16 QAM 15 megabits per second. Obviously, yes, there's a slight difference in the actual field strength contour that's required for reception, the minimum usable field strength. Okay, and then we also yesterday just looked at, if we look at DVB-T, and we're looking at similar field strengths, and here we use 84.4 and 84.6, and we look at T2, and we've got 64 QAM. In T1, we've got 16 QAM, and we've got a slight different guard interval. But this is the same actually in kilometers for the T2 versus the T1, T2 versus T1 standard. And then you've got the same code rate. You've got normal, not extended. And then we again sit there with a much bigger capacity with the T2, which just highlight the importance of T2 and the advantages you're getting from it. Okay, so then also just looking at T1 and T2, one can just see that if you look at the modulation, yes, both is COFDM for the QPSK and the 16 QAM, and then but you can go up to 256 QAM with T2, which gives you definitely more capacity together with the other parameters. Then it can be implemented in band 3, band 4, band 5, and here it can also be implemented in the L band. You can see there's more options, 5 megahertz and 1.75 for T2. And then obviously the coding for forward error correction is extended and changed in the T2 version with some other combinations. The FFT size, there's more options with T2. The carrier to noise is also different in the two setups. And then also you've got one pilot pattern in T1 and 8 different ones in T2. And then there's a huge improvement is the number of guard intervals that you can actually, and the timing associated with the guard intervals. So there you can see for T1, you only have a maximum of 67.2 kilometers in the 8K mode, and with T2, you can go up to 159 kilometers guard interval, which give you much larger SFNs that can be implemented for T2. Okay, then on the signal bandwidth, yes, it's slightly different for the different bands that's being used. So specific robustness is very limited in T1, where in 2T, you have these physical layer pipes where you can have different programs with different robustness, etc., between on the same multiplex, but defined as individual physical layer pipes or PLPs. And then very small interleaving is possible with one OFDM symbol is performed. And then if you look at T2 interleaving depth from 70 milliseconds in mode A, single PLP, up to more than 200 milliseconds mode B. Okay, and then also if you look at SISO and SIMO, which is available for the receiver on T1, and with T2, you've got also SIMO and MIMO available for the diversity receiver. Okay, then rotated constellation, which gives you a specific amplitude and direction, is not available in T1, but it's available in T2. And then more extensions is available in T2. If you look at the maximum bit rate, yes, you can get to 31.7 megabits per second in T1, but in T2 you can go up to 50.3 theoretically. Then the used bit rates for the different reception is also quite a bit different, and you can see there's higher, you can achieve higher bit rates than with T2. Okay, and then yes, anyway, when you introduced, when T2 was introduced, there a lot was done to actually keep it within the same sort of mask to ensure that there's compatibility between the two and there's not huge interference cases. Okay, most of these were mentioned before. And then, the multiple PLP capability. And here it's just demonstrated that you can actually have in one multiplex, you can have PLP1, PLP2, PLP3 with different transmit configurations. Okay, so the advantages of T2, more coverage, same coverage with less bit rate, same bit rate, even 6 dB less, and then a power reduction. Okay, then, yes, we've had analog TV, we've had DVB-T, we had DVB-T2, we've got DVB-T2 high definition, but then also with MPEG 4 at T2, and then also with MPEG or HEVC, which is arriving anyway at your as the transport stream or as the stream that goes into the transmitter. And then obviously there's a question on if there will be any further enhancements on DVB-T2. Okay, then just some comments. No major improvements in noise performance in future. Channel coding and modulation close to the theoretical limit, the Shannon limit. So video processing, is evolving faster and has still significant potential for improvements. And there they are looking at future video coding, which can be a huge improvement in capacity. Then, yeah, obviously, new trends is 3D, TV, and then I think one can also see it with virtual reality, etc., which is also improvements. And then high-resolution 4K transmissions. Okay, then if we just look at ATSC3 and we look at T2, so we can see, yes, there's a slight improvement from ATSC3 over T2. You can also see it here that there's a slight improvement in the capacity, and your ATSC3 signal is much closer to the Shannon limit, which is the theoretical limit of capacity. Okay, so if we do a comparison then between T2 and ATSC3, we will see, yes, the forward error correction and the LDPC coding is expanded. There's many more options to choose from with the forward error correction. Modulation, you can see there's much higher modulation rates that can be achieved. There's not so many FFT combinations that can be used. And then you can again see differences in the guard interval, which will give you more options for the different size of networks that you want to, and density of the networks you want to deploy. Okay, then you can see here that the minimum and the maximum data rate that can be achieved with T2 and then also with ATSC3, it's definitely higher that can be achieved with ATSC3. Yeah, and the signal to noise operating, signal to noise ratio is also quite different between T2 and then also between ATSC3. So ATSC 3.0 is based on DVB2 transmission technology. So there's very similarity. We've done measurements on both of these systems with drones, and the measurement of the power in the that's being transmitted is done with basically the same configuration. It's only when there's changes in the full bandwidth that you need to adjust it, but you need to adjust it anyway for T2 with being implemented in different frequency bands or frequency bandwidths as well. Then DVB-T allows for MPEG-2 transport stream, multiplex as well as IP streaming in the PLP. ATS3 is using non-uniform constellations. DVB-2 is using traditional QAM. And then DVB-T2 is well spread and proven all over the world over the last 15 years. And many receivers are available. But from what we've seen in the US, yes, there's also many receivers available. I don't think that's where there's any problem on the receiver side. Yes, DVB-T2 is definitely more proven. It's been out there for a longer time. And both DVB-T2 and ATSC3 allows use of modern source coding algorithms. Okay, so that is just a quick overview on T1, T2, and ATSC3. Any questions on this? Okay, there's a question here regarding DVB-T2 and 5G broadcast. I've had a little bit of experience with 5G broadcast, but I can't claim that I'm an expert on 5G. But however, if one look at 5G broadcast currently, it's still not 100% 5G broadcast. It is still linked to LTE broadcast. What we've learned is that the 5G broadcast will, for the next few years, concentrate on maybe 3 to 5 years. They will concentrate on mobile and portable handsets because at this stage, it seems as if well, it's not 100%. They're not right there to look at fixed reception in 5G broadcast where we stand right now. It will be focused on the smaller handsets with smaller screens, etc. And then that will probably only in about 3 to 4 years or so change, where the focus will be more on fixed reception. The limitation, as far as I understand it, is that the current networks are not really geared to run a full 5G broadcast to individuals because of the capacity, and then also because of the actual problem of having very large screens and having large capacities to feed very large traditional fixed reception environments. So that's what we got recently from a discussion, a workshop from Roda and Swartz that was, that we attended, yeah. So yes, so what was also said during this discussion with Roda and Swartz, where there were a number of international players, they indicated that currently T2 and ATSC3 is the medium that will carry most of the fixed reception broadcast for the next 5 years at least. It will only be, there will probably only be a successor that will compete with that after 5 years from now. Okay, I can continue then with the next short presentation, which is general comments on the full implementation of a T2 network and different aspects that need special attention in order to make the 5G, to make the DVB-T2 deployment successful. If there's no more questions, I can continue with that. Okay, if we look at the steps that need to be taken in the implementation of DVB-T2 or DTT, there's a few things that need to happen and that one need to agree on to ensure that the actual implementation is going to be a success. So what we found is that in many countries there's huge expectations on what's going to be transmitted and the variety that's going to be available regarding programs, the number of MUXes that's being set up. And all of that in many countries is not addressed in detail. There are no, from the regulator and from the ministry's perspective, there's never a clear view on how much capacity is really required, how many channels need to be coordinated, how many programs need to be transmitted. So there one really need to look at the number of national MUXs, the national number of regional MUXs. You need to look at free-to-air services. You need to look at subscription. You need to look at PBS. You need to look at the private services. You need to look at the community services. And this all need to be done holistically. And there need to be a plan from government side and from the regulator side to introduce this and then convert this obviously into a requirement to ensure that the frequency plan that's being developed is adequate to provide the number of services terrestrially. At the same time, I think one also need to look at what the future is going to demand. If we look at 5G, of which lots of effort in 5G is all linked to automation of vehicles, then you are also not only looking at the automation of vehicles, you're also looking at new entertainment systems in vehicles that can drive themselves and that the entertainment fit a vehicle which has got people inside, where there's no driver, and everyone can watch maybe different programs. So these programs can obviously be coming through the internet that's available, but it can also come via the terrestrial network, especially if you look at DVB-T2 Lite, which is more catering for mobile services. So I can't emphasize enough that all of this need to be in place, and there need to be regulations that actually stipulate this in order to ensure that the frequency plan that's being developed can fulfill all the requirements that will be placed on the regulator and on the signal distributor. So if we look at broadcast, the regulator and regulations, before any of these developments can really happen or transmissions can happen, the regulations need to be prepared for licensing of the different program services as we defined above. We need to look at the multiplex operators, and we need to look at the signal distributors. And all of that need to be in place to ensure that there's no uncertainty on what licenses is required and anything that will hamper deployment of the actual network. So there's really a lot of work on government side and on the regulatory side to ensure that it's a seamless, organized manner in which the network is deployed, with special targets from all the sectors that's playing in that environment of broadcasting. So once all of these is in place and you know what the requirement is going to be, it's the requirement from the regulator together with the administration to ensure that the frequency plan is produced, and this frequency plan can be produced either on a regional basis or on a countrywide basis, or it can be coordinated from the start with the neighbors. We had an exercise in Southern Africa where we got all the regulators in SADC together, it was the majority of them, and we had a conference at the airport where we, within 1 week, produced a plan that was more or less accepted by most of the regulators. I believe that was extremely successful But what I can admit is that I can't say that all the items mentioned above was in place, but we at least could produce a frequency plan which was developed in a format that it could be coordinated with most of the neighboring countries. That speeded up the process anyway from a coordination perspective, where when the SADC countries left the meeting at the end, all the discussions was already done, and it was basically a formality to get the plans coordinated. So I think if in the Arab states, you probably have a similar situation where you can go about in doing it in that sort of format, where you do all the coordination with the countries and make sure that from day one, you've got a plan that can easily be coordinated without any unhappiness between different parties regarding interference. So the plan that we developed here was, they called it, or we called it, the 7 MUX plan. And the 7 MUX plan allowed for 7 MUXes in the frequency band that's available. And that was then a plan that was, it had reused distances with neighboring countries, that it could actually be implemented in all neighboring countries. But it also allowed for some space right there on the borders to ensure that we don't end up with too many coordination agreements between the countries. The plan could have been improved as well. There was a big concern at the time regarding SFNs, because no one was really familiar with the use of SFNs, and there were a lot of arguments that the SFNs are going to cause a lot of interference. And finally, all these SFNs, or most of them, are now implemented on a provincial basis. So there's 9 provinces, and the frequency changed from province to province. And we had 4 groups of frequencies that was distributed. So in all cases, we had enough protection between co-channel and adjacent channel assignments, which eventually caused no problems. And even with the different landscapes, moving from very flat areas, large flat areas, to very mountainous areas, to coastal areas, the SFNs has now been tested, and it all run well without any self-interference. And if you want to add a station, it's actually very easy, because we've allowed for enough frequency allocations at every 67, around about 60 kilometers from one another. Okay, so much about the frequency plan, but the frequency plan is definitely extremely important, as that need to be coordinated with the neighbors and then also registered with the ITU. So at the time of doing the frequency plan, we obviously also looked at coverage, and we ensured that adequate coverage was achieved. And the target was around about 90% coverage. And that could be achieved with a network with a capacity of about 22 megabits per second, which give you 22 standard definition channels, or a combination thereof, per multiplex. So yes, there's definitely even further improvements, because it's not necessary to have 7 MUXs in a 7 MUX plan for 9 provinces, and do your network design on a provincial basis. With the flexibility of T2, you can have one single frequency network that is right across your country, and there shouldn't be any interference cases if you keep your guard interval large enough. So yes, in this coverage plan, you obviously need to agree on the population that need to be covered. You need to look at complementary coverage, which is coming from satellite services. You need to look at your program feeds, and then you obviously need to look at what do you want? Do you want standard definition? You want high definition or ultra high definition services? Because that has got a huge impact on the number of programs per MUX that you can run. So you can probably run maybe about 5 or so high definition services with 20 megabits per second. But you can also have a combination of standard definition and high definition services, and even you can then also look at your portable services that you want to run for T2 Lite. Okay. What is important is that during the deployment of such a new network, you need to have an online information system, and I think the best to call it is My Best Server or something alike, which will tell all the viewers out there what the latest information is regarding the network deployment. So you should have maps on there which give you the information up to street level of which house that's got coverage, which transmitter site it should aim its antenna on, and that will be of huge help also to the actual installers. So other information that need to be included on this online help facility or My Best Server facility is on-air dates of transmitters, switch-off dates of the analog services, because you will have both analog and digital running at the same time. You should have your best server information. You should have information on uncovered areas that to ensure that the installers and also people doing their own installations are not looking for a signal while it is an uncovered area. And that should easily be picked up just going onto the web and having this first-hand information, first-hand updated information online. There should also be technical assistance on how an installation should be done, where the receivers can be obtained. There should be guidelines on what the best practice is for installation. And then what we found, we simplified the process by not using channelized antennas anymore, but using one antenna that can be used for any part of the band. Nowadays it is simpler because most of the countries only use up to channel 48 or 694 megahertz from channel 21 or 470 megahertz for the transmissions. Apart from that, there's also the responsibility on the regulator and also the operator or signal distributor regarding the receivers. many times there's the country gets flocked with receivers from low quality, etc., and which is very cheap. But in some cases they cannot conform to this transmission standard that's being followed, or the transmit configurations. So all these receivers need to go through a thorough testing to ensure that they are type approved, and that when they arrive in the country, they will be implemented without any difficulties. So then apart from that, it's not only the receivers, it's also the receive antennas. You will find many receive antennas being distributed, saying they are adequate to receive the program. But what one need to look, when you do your planning, you will focus and have your coverage design based on a typical receive antenna with a certain number of dBs of gain. You will also make sure that you use cables that hasn't got too much cable loss. So it need to be a good cable that will ensure that you've got coverage and that you can receive the coverage in accordance with the whole network design that were done by the regulator or by the consultant for the country. So there's definitely responsibility on the regulator and the signal distributor to ensure that the receivers that's distributed will fulfill the requirement. We went through a national inspection of all manufacturing facilities in South Africa to look at their receivers and to ask for type approval documentation that we could ensure that it comply not only to the regulatory type approval, but also to the type approval of the South African Bureau of Standards, which addressed various aspects. So it addressed the RF aspects and the receiver sensitivity of the receiver, as well as the compatibility with the transmit configuration. Then in addition to that, it was also addressed the safety aspects, which is mainly related to health and safety and electricity. And then it was also evaluated in accordance with its general operation and ease of operation. So that responsibility need to lie somewhere, either at your regulator or your operator, to ensure that there is a specification that need to be complied to. Obviously, during this whole design process, there's also the whole design of the network. And we had this one slide earlier today where we looked at antenna gain, transmitter power, feeder loss, cable loss, connector loss, and all of that. And we eventually came out with a transmitted power specification in accordance with the ERP that appear in the broadcast plan for the country. So it's important that someone takes the responsibility to ensure that the plan that's produced does not only represent the coordination issues regarding the limited ERP that's being coordinated. It also needs to include more aspects regarding critical mass filters that need to be introduced. It needs to look at each antenna gain. It needs to look at the feeder cables, and this assist the actual signal distributor to produce a bill of quantities, and then from that bill of quantities produce a cost summary for the full network implementation, because such a network will definitely cost millions of USD, and one need to make sure that there's no uncertainty on what the network is going to cost. At the same time, that those costs need to be available, that can be also be shared with government, and that whoever is funding the project, that the money will be available on time. Because with government, sometimes these budget periods, it might be running over a 3-year period, and you need to have this information with government maybe 2 years because the funds will be released, 2 or 3 years before the funds will be released. So yes, it's a huge effort, and all of that need to be available. So obviously, at the same time, one also need to prepare a national implementation plan, and this national implementation plan will have timelines for implementation as well as interim goals and the final implementation target. All of this need to be communicated to the viewers out there. And this don't only apply to the new services or the T2 services that's being implemented, it should also apply to the analog services that's being switched off, that people know when the analog service will not be there anymore, and that they, by that time, should have acquired a set-top box or integrated television set, a DVB-T2 integrated television set that they can use for reception. So apart from that, there need to be a national plan and a national campaign for DVB-T2 implementation, and government support and all the player support need to be there. If that's not the case, your implementation is not going to be a success. The time frame should also be realistic. It should not be, there shouldn't be delays. People should have a seamless transformation from analog to DTT, and that will make it much easier for everyone to accept the new standard. Otherwise, it just drags on, and people find other ways of fulfilling their entertainment requirement. So, as I've said earlier, yes, we also need to ensure that the funding requirements are communicated with government on a time-years basis, that the funds is available, and in line with the government financial budgeting for this. It will also assist other players to come up with better schemes and incentives to ensure that the network is implemented successfully. Okay, then, I've mentioned that, yes, we need to perform testing on the receivers, define a national receiver specification. That will all ensure compatibility of the system for the country. And many of the systems failed or implementations failed because no receivers were deployed. I can take an example from Botswana, where they implemented ISDBT. The ISDBT receivers was not available, and they have now started to convert some of the intention seemed to be that they will convert some of the ISDBT transmissions to DVB-T2 transmissions. Main reason for that is that they're the only country in this area having ISDBT, and everyone else has got T2 receivers. What we've seen in other countries is that there's only there's a lack of programming available in the country, and then the broadcaster and the signal distributor launch their complete service, but because there's no variety and only 2 or 3 programs on the set-top box that can be received, people decide to use other avenues like satellite TV, etc., to ensure that they've got the necessary variety of programs to watch. So there's many pitfalls in the implementation of a DTT network, and I can't emphasize enough that one need to plan thoroughly and go out of your way to ensure that the network is well planned and well communicated amongst everyone within the country. And yeah, that's the final presentation. You are welcome to ask questions on any of the topics so far. Okay, so there's a question on T2 and ultra high definition or 4K. I haven't seen it being deployed locally. I think it is possible to go for to transmit the content. That will happen on the studio side, and the studio side can provide the transport stream. It will take more space on the multiplex, but it shouldn't be a problem. It can be handled by the transport stream. So it will, like we've looked at and we said, HVEC will be replaced in future by more effective algorithms. And so, yes, I think everything is possible. There's lots of development as well on the IP side, because eventually it's an IP stream going into the transmitter. And yes, it's a matter of just making sure that the receive equipment can handle the transport stream. Okay, I will just check the abbreviation for the successor of the HVEC, but there is a replacement for that, and I believe there's lots of development going on that side of the program itself. Yes, so as I understand it, yes, it is supported. I haven't seen any of our broadcasters currently using that, but I don't think there's any technical reason why it can't be supported, because it's just more data. Whether it's going to make sense if there's not a huge reduction on maybe on the MPEG or HVEC side, you're just going to sit with a very limited number of programs per MUX, because the multiplex can only handle a certain number of megabits per second. And so if we are looking at, say, 4 to 5 megabits per second for an HD program currently, and we are looking for a 4K system which is maybe double, you can only transmit 2 4K or ultra high definition programs per multiplex, which don't give you enough variety on such a stream. But if I look at MultiChoice in South Africa, they changed from MPEG 2 to MPEG 4 to HVEC, and that was some development that all happened on their side. So there's no reason why it can't be changed to to 4K and other ultra high definition capabilities, yeah, or technology. Any more questions or anything else that you want more information on?
I have a general question. How I can calculate the interference from an allotment?
So yeah, how can you calculate the
Interference
yeah?
from an allotment, a polygon.
Look, if you just have this this polygon, and it can be done in as I've said, a polygon or a single frequency network can be registered in two ways. So the one way is to register it as a number of SFNs, a number of assignments with the same single frequency ID, or it can just be an allotment area. If you have to do it probably at the level, and if we use a tool to do that, I will just look at the combined field strength, obviously setting the, if I just want to look at interference, I will go for 1% of the time. So I will look for the unwanted or the interference calculation, and you can then produce it over the whole area with the actual transmitted levels. I know there is another procedure for the allotments, but I can also just look at that and I can provide you with that. I've got a few questions here that I will respond to, and I'll just relook at the allotment area and the coordination thereof.
I have the second case, the area. I don't know the transmitter, the station.
Yeah, there was a procedure during. Sorry, I can't recall it now. There was a procedure for on how to create this allotment or polygon, and I just need to go back and relook at that. I can't recall how it exactly was done, but there were a procedure defined for that, to say how you should limit it right on the edges of the polygon.
Thank you.
So I will send this to Mr. Ibrahim, and I'll ask him to distribute it to you. Okay, maybe just a question on, maybe it's just a general term for the follow-up of HVEC. They just say future video coding. So there's nothing definitely for it, but there's lots of video processing is evolving faster, and there's still significant potential for improvement. So there's definitely a lot of work being done on further video coding and processing. Okay, I think that's all from my side. I don't know who should close the procedure, but yes, I think that was more or less the full presentation as we agreed. Okay, thank you then. And thanks for your participation and the questions, and good luck with your network planning and T2 planning. And as I've indicated, I will provide the answers that's still outstanding.
Hello, sir.
Yes.
Really, I'm so happy to attend this course. On behalf of the union, I extend thank you for training course, and we hope we will meet another course and more collaboration is coming day soon.
Thank you very much. And yeah, thank you to you all of you. Okay.
Thank you. Thank you,
Okay.
sir.
Enjoy the rest of your day.
Okay, goodbye.
Okay, bye-bye.
Thank you. Bye-bye.
Bye.